Welcome to Websoft Solutions Australia. If you like our content, please consider subscribing.
In this part, we'll use Wireshark to detect issues with network communications, including, above all, those that indicate the attack is taking or have taken place, or errors in the configuration of the network services. We'll first discuss the features of the program in detail. During the training, we will use version 1.6.4. If you'd like to do similar exercises by yourself, please use this version or higher. Newer versions are backwards compatible. Since this is a network monitor, it should, first and foremost, capture information sent through a network. Wireshark is able to collect various types of data sent through various adapters connected to your computer. In our case, it's a network card. As we've mentioned in the theoretical part, these can also be Wi-Fi adapters. In Wireshark, you can configure a few options related to the adapter. Please note that you can collect data from a remote computer. Wireshark allows the capture of data sent by another adapter on the computer you're connected to. This functionality works only in the Windows environment, although Wireshark is available in other platforms too. You can choose the type of network. We're working with the Ethernet networks. You can choose to capture data in the promiscuous mode. Wireshark can put the network card into promiscuous mode. The wireless settings button is inactive because Wireshark hasn't detected any compatible adapter, such as the AirP cap. The data collected can be saved in one file or in a couple of files. You can specify the rules according to which the data will be divided. In the lower left corner, you can see the settings that allow you to determine in which circumstances the data capture should stop. It is not necessary to sit before the screen watching Wireshark collecting data. Capture filter is an option used to set the data capture filters. We have already mentioned that you ought to be careful with those filters. You can use them when you want to diagnose a specific situation or a particular problem. For example, to collect the data addressed only to TCP port 80, the HTTP protocol data, or to examine the communications of a particular host. While collecting data in order to create a baseline or to make sure that everything is working normally, you should not use data capture filters. There are also a few display and name resolution options. As we've mentioned, you should turn these off in case the program cannot cope with the stream of data. The Start button starts the monitoring process. As you can see in the picture above, we don't have to generate any additional traffic yet. Let's select a packet to get a look at the program interface. In the upper window, we see information about the captured packets grouped into columns. The information available includes sequence number. The number of the first packet captured is always 0. The next grows sequentially by 1. The next column shows the time elapsed since beginning of capture. Often, we would like to see this in a different layout. Frequently, we're interested in how much time passed since the previous captured packet. Sometimes it makes it easier to find some abnormalities. In other columns, we see the sender IP address, the receiver's IP address, the protocol, as long as Wireshark is interpreted correctly, and the amount of data and diagnostic information. Let's see how all this looks for an application layer protocol. For example, let's select the HTTP protocol. After typing a valid display filter, we will only see HTTP packets. We can see the Ethernet frame, and at the bottom we can see the whole set of captured data. The frame contains everything that we would find in the higher level protocols. When we choose the details of IP version 4, we can get to know the values of the IP version 4 header fields. For example, time to live is 64, which means that the package was, most likely, sent by the server running under Windows because these systems, in the case of the local networks, ascribe 64 as the initial TTL value. We can also find out by whom and to whom the packet was sent. Examining one level higher, we find the TCP protocol. We see that this is a packet sent to port 80 from a dynamic port higher than the port 1024. We can see the sequence numbers and acknowledgement numbers. That is, numbers that allow the TCP protocol to make sure no data has been lost during the session. There are also the TCP header options. These are the flags which, as we said, are set in a strange way during the Xmas tree scan. The checksum closes the TCP header. When it comes to the HTTP protocol, Wireshark analyzes it just like any other header values. We get to know that it was a server's 200 OK response, a message confirming a successful client request. To try out more Wireshark functions related to HTTP protocol, let's visit a website such as youtube.com. From the perspective of a user, this site gives you an opportunity to view a variety of contents. Let's see how it looks from the Wireshark's perspective. Let's clear the filter field. If the data is not cached yet, we'll be able to see the data downloaded by the client. Looking at a stream of packets, it's hard to say what we're actually seeing. So let's apply some additional features offered by Wireshark. In the File Export menu, you can select objects from the HTTP session. Now we can see that these were some pictures. Wireshark has a sync option so that everything that's displayed in an additional window is highlighted in the main one too. We can even save the pictures that have been captured. After the reassembly of the right packet, you can do the same with other multimedia files. If you have a program that plays Adobe Flash video files, you can watch offline what you've previously watched on the internet. While exploring other functionalities of Wireshark, we'll examine some problems. Let's start with a classic problem. We close the window we've been using and start the program with a capture file we've saved before. Because we're now dealing with the ARP protocol, a lower layer protocol, the analysis is much simpler. ARP converts IP addresses to MAC addresses and vice versa. There's little data in the ARP packets. The minimum and maximum size of the Ethernet frame is specified. If there's too little data to reach the minimum, the frame must be filled up. Programs sometimes fill up the frame with current buffer content. Evidently, this is a network card driver problem. It fills up the frame with what's in the buffer at the moment. For example, with what the user has last received or sent over a network. Analyzing the ARP, you can find out what network users have been doing recently. Let's see how much information we can get from DNS. We can choose the protocol we're interested in and corresponding field. In our case, it's source. When you click on it with the right mouse button and choose Prepare as Filter option, you can create more complex filters. Now we can observe the DNS communication of the chosen client. After a short time, we'll be able to tell what programs have been running on the computer and what its users been doing. The DNS is a protocol that can give us all of this information. As you can see, to connect to a device in the network, you must first get to know its address. You must first send a request to the DNS server. Let's see another example. We've captured data concerning network users. In this case, someone is connected to HTTP servers. To get a general overview of what happens in a capture file, let's start with the Statistics menu. We'll examine the HTTP statistics and the packet statistics. You can apply data filters to the statistics too. In our case, we will create the statistics based on all the packets. The capture file contains the following information. The client we've chosen sent 144 GET packets. This is 100% of the activities performed by the user. We see the responses below. Is there something in these responses that may be troubling? Not necessarily from the security perspective, but from the management perspective. Let's have a look at the HTTP server's responses. Right now, we don't know what servers they were or what happened to the data. We see 140 responses, out of which there were 80 OK responses and 57 redirection responses, where a server responded to a client that some data had been moved to another location. Interestingly, the not found message of the HTTP protocol indicates a client error. The client wanted to connect to something that doesn't exist. The server isn't responsible for the missing content. We can analyze the data using various statistics. For the same item, let's see the endpoint list for TCP. It turns out that servers redirected our requests not only to different addresses, but also to different ports, so we're not able to trace the data. We managed, however, to generate a list of IP addresses of hosts that were involved in the communication. From the number of packets generated by the host, we can guess that the selected address is the client's computer. The list contains the IP addresses of all computers we were redirected to. Let's see what other information we can get from the DNS server. Let's open a file with the data captured when the computer was starting up. An interesting experience is to monitor the computers left unattended, that is, those with no one at the keyboard. What does the computer do when no one uses the keyboard? Some of the programs installed on the computer are very chatty. Particularly interesting is what happened with the computer when it was starting up. We know that to find out who the computer was connected to, we should filter the data for the information from the DNS protocol. We can see that the computer has the McAfee antivirus installed on it. We also see that the program tried to perform an update. Next, there is a query sent to the virtumode.com server, which isn't a McAfee server. If we did some research about this server, we would learn that this is a website that virus is connected to get instructions concerning further actions. It was the site used to coordinate attacks. Normally, the detection of such a situation is not all that easy, but the capture file and the filter on the DNS server will show us all such information. If you learn that the computers you look after connect to the websites that you know nothing about, check them out, and everything will become clear. To achieve all this, we only needed to know how to use Wireshark for data capture and how to filter this data according to simple rules.